Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Martin Rees 1973 paper, Black Hole Models for Active Galactic Nuclei, stands as a pivotal contribution to astrophysics, marking a significant advancement in our understanding of the enigmatic phenomena observed in active galaxies. These galaxies, characterized by their extraordinary luminosity and energetic emissions across the electromagnetic spectrum, had presented a formidable puzzle to astronomers for decades. Rees' work, appearing in an era when the very existence of black holes remained a topic of considerable debate, provided a compelling framework for explaining the prodigious energy output of active galactic nuclei, or AN. By invoking the presence of supermassive black holes at their the genesis of Rees' black hole model can be traced to several key developments in astrophysics and theoretical physics during the preceding years. The discovery of quasars in the early 1960s, objects with immense redshifts indicating vast distances and correspondingly enormous luminosities, posed a significant challenge to conventional energy generation mechanisms. Similarly, the Seyfert galaxies, identified by Carl Seyfert in 1943, exhibited intense emission lines and compact, bright nuclei, intimate unusual activity occurring within these galactic centers. These observations suggested the existence of a central engine capable of generating tremendous amounts of energy within a relatively small volume. Theoretical considerations also played a crucial role. The burgeoning field of general relativity, spurred by the work of physicists like Roger Penrose and John Wheeler, led to a deeper understanding of black holes as predicted by Einstein's theory. The realization that black holes could, in principle, extract energy from their surroundings through processes like the Blandford-Sednagic mechanism provided a theoretical basis for the energy generation in AGN. Furthermore, the development of accretion disk theory by Nikolai Shakura and Rashid Sunyaev provided a plausible mechanism for fueling the black hole with infalling matter, converting gravitational potential energy into radiation. Rees' 1973 paper synthesized these diverse strands of astronomical observation and theoretical understanding into a coherent model for AGN. The central idea involved a supermassive black hole, with a mass ranging from millions to billions of times the mass of the Sun, residing at the core of the active galaxy. Gas and dust, drawn in by the black hole's immense gravity, formed an accretion disk swirling around the black hole. As matter spiraled inward, it became intensely heated due to friction and compression, reaching temperatures of millions of degrees. This superheated gas then emitted copious amounts of radiation across the electromagnetic spectrum, from radio waves to gamma rays, accounting for the observed luminosity of AGN, a crucial aspect of Rees' model related to the efficiency of energy conversion. Unlike nuclear fusion, the primary energy source in stars, accretion onto a black hole could, in principle, convert a significant fraction, potentially up to several tens of %, of the infalling matter's mass into energy, according to the equation E equals mc squared. This high efficiency made black hole accretion a far more plausible explanation for the extreme luminosities of quasars and other AGN. The paper also addressed the issue of variability in AGN. Active galaxies often exhibit rapid fluctuations in their brightness, on timescales ranging from hours to days. Rees argued that these variations could arise from inhomogeneities in the accretion disk or from episodic accretion events. Such fluctuations provided further evidence for the compact nature of the central engine. One specific technique employed within Rees' work involves the application of general relativistic equations to model the accretion process around the black hole. For instance, the paper considers the Novikov-Thorne model for thin accretion disks, which incorporates relativistic corrections to the Newtonian treatment. This framework allows for the calculation of the energy flux emitted from the disk as a function of radius, taking into account the effects of spacetime curvature near the black hole. The resulting equations, while complex, provide a detailed picture of the radiation spectrum expected from an AGN. The immediate impact of Rees' paper was substantial. It provided a unifying framework for understanding a diverse range of observations related to active galaxies, ranging from their high luminosities to their rapid variability. It also stimulated further research into the physics of accretion disks, black hole spin formation of jets, collimated streams of particles emanating from the vicinity of the black. Later use and evolution of Rees' model have been extensive. Subsequent studies refined the model by incorporating more detailed physics, such as the effects of magnetic fields and radiative transfer. The development of numerical simulations allowed researchers to model the accretion process in 3 dimensions, capturing effects such as turbulence and instability. The observations from space-based telescopes, such as the Hubble Space Telescope and the Chandra X-ray Observatory, provided unprecedented images and spectra of AGN, allowing for detailed tests of the black hole model. The Blandford Payne mechanism, proposed in 1982, offered an explanation for the formation and collimation of jets. This process involves the extraction of energy from the rotating accretion disk through magnetic fields that thread both the disk and the black hole. This mechanism is closely related to the Blandford-Sednagic process, which extracts energy directly from the rotating black hole itself. These models, building upon Rees' original work, provide a comprehensive picture of the energy generation and transfer in AGN. Despite its success, Rees' model faced some initial critiques. One concern related to the origin of the supermassive black holes themselves. How could such massive objects form in the early universe? Various scenarios have been proposed, including the direct collapse of massive gas clouds and the mergers of smaller black holes. The supermassive black hole binary candidate system in the galaxy OJ287 presents an example of the ongoing research into the evolution and dynamics of these behemoths, with two black holes with a mass of 18 billion times the mass of the Sun and 150 million times the mass of the Sun, revolving around each. Another challenge involved the details of the accretion process. How does matter lose its angular momentum and spiral inward toward the black hole? What is the role of turbulence and magnetic fields in the accretion disk? These questions continue actively investigated by astrophysicists. The contemporary reception of Rees' paper was largely positive. The astronomical community recognized the significance of the black hole model as a potential explanation for the enigmatic properties of AGN. The paper stimulated a flurry of research activity, both theoretical and observational, aimed at testing and refining the model. It cemented Rees' reputation as a leading figure in astrophysics and cosmology. The work of Donald Lynden Bell, particularly his 1969 paper suggesting the existence of massive black holes in galactic nuclei, served as an antecedent to Rees' work. Lynden Bell's paper emphasized the possibility of accretion as a source of energy, which provided a key conceptual foundation for Rees' more detailed model. The accretion disk theory of Shakura and Suneve, published in 1973, provided essential physics for the operation of quasars, with researchers like Pringle and Reess highlighting the role of viscosity in these disks. The work on viscosity allowed for the effective transfer of angular momentum, enabling the efficient inflow of material toward the central black hole. Rees' model exerted a demonstrable influence on numerous subsequent works. For example, the work of Roger Blandford and Roman Sednagic on the extraction of energy from rotating black holes built directly upon the framework established by Reess. Their work on the Blandford-Sednagic mechanism provided a theoretical explanation for the observed jets emanating from AGN, further solidifying the black hole model. Furthermore, the observations from the Event Horizon Telescope, revealing the shadow of a black hole in the galaxy M87, represented a triumph for Rees' model, confirming key predictions about the nature of black holes and their surrounding environments. In conclusion, Martin Rees' 1973 paper, Black Hole Models for Active Galactic Nuclei, represents a watershed moment in the history of astrophysics. It provided a compelling and remarkably prescient explanation for the prodigious energy output of active galaxies based on the presence of supermassive black holes at their centers. The model, while refined and extended over the years, remains a cornerstone of our understanding of these fascinating objects. Its influence extends far beyond the specific topic of AGN, having stimulated research into black hole physics, accretion disk theory, and the formation of jets, shaping the course of modern astrophysics. It is a testament to the power of theoretical insight, combined with careful observation, in unraveling the mysteries of the universe. And, perhaps, it also serves as a reminder that even the most outlandish ideas, such as the existence of these cosmic vacuum cleaners, can, with sufficient evidence and a dash of intellectual bravery, become the cornerstones of our scientific understanding. The initial incredulity surrounding black holes, concepts so alien they seemed ripped from science fiction, highlights the inherent human tendency to resist paradigm shifts even when confronted with compelling evidence. However, Rees' work, along with that of his contemporaries, played a crucial role in transforming these once speculative objects into accepted astrophysical entities.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.